2.1a is describing location in a distribution. So suppose Malcolm earned an 86% on his statistics test. This is suppose, all right. Should he be satisfied or disappointed with his performance? Well, that depends on how the class did, right? So we're going to look at stem and leaf plot. No, it is not an actual stem and leaf plot. Okay, so what we're going to look at is how many scored below him out of the total. So in our stem and leaf plot, Malcolm's grade is right here, okay, 86. And we want to look at the total number that took the test and how many are below. So notice all the ones that are in red are how many people scored below Malcolm's. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21 people scored below him. So you're only counting how many are below his score out of the total. So it's 21, 22, 23, 24, 25. So 25 total tests. So 84% of the class are below. Okay. So the way that we answer this question is Malcolm scored at the 84th percentile. Okay, that word at is important. That's how we say it. You scored at the 84th percentile. So basically, he's above 84% of the class. So percentile is a new definition for you guys. The pth percentile of the distribution is the value with p% of the observations less than it. Now, some people calculate this where they include the observation, but we're always going to do it where we don't. It's always count how many are below. Okay. So let's find the percentiles for the following people. These are not real grades. Taylor, geez, she hasn't even taken it yet, so I didn't feel too bad. All right, Taylor scored a 72. So let's see what percentile she's at. So 72 is right here. 72. How many people are below Taylor? One person. All right. One person. So not so good. Okay, 1 out of 25. So only one is below. So what percentile did she score at? The 4th percentile. All right, or just 4%. What I should say. All right. Jet, who scored 93. Way to go. All right, now, just because Jet is right here at the top of the class in this example, does that mean 100% right there? Nope. How many people are below him if he's right here? 24. So we have to calculate it as 24 out of 25. So he really only scores in the 96th percentile because that's, or at the 96th percentile because that's how many are below. Yes?
So what if there were multiple 93s, like 4 or 5 93s? How does that work?
If there are multiple, you only count below that grade. You start counting at what? 90 and below. Yep. Yep. If you have multiple scores, you still just count the people below. So, for example, 2 students who earned scores of 80. Okay, so 80 is right here. There's 2 people. We still count how many scores are below 80. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12 people are below 80. Even though there's 2 scores of 80, it's only how many are below. So those people both scored at the 48th percentile. All right. All right, so relative frequency graphs. Now we're going to do cumulative relative frequency graphs. So remember, frequency was just count. Relative frequency was the percent. And cumulative, we're going to add on as it builds. So for this one, we've got some data. The ages of the first 44 presidents when they took office. Okay, ages of the first 44 presidents when they took office. So first we just have our count, our normal count. So we've got 2 presidents who are 40, 44, 7 who are 45, 49, 13, etc., etc. Okay. So that's just frequency. So we know probably, hopefully, how to convert this to relative frequency. So we'll start with that and make a column. So you guys can write this down so you have this. Anybody know how I find the relative frequency for 40 to 44? You guys should know this, Ginger. Yeah, 2 presidents out of the 44 presidents that we have in our data. So 2 out of 44 converts you guys to 4.5%. Okay. And then for the next one, again, it's just relative. We're not doing cumulative yet. So we would just do, this one is 7 out of 44 total. And so we get 15.9% of presidents who were 45 to 49. Okay, and the next one, 13 to 44. And so we get 29.5% of presidents who were 50 to 54 when they took office. And 12 out of 44 gives us 27.3% of presidents. And 7 out of 44 again is 15.9%. And 3 out of 44 gives me 6.8%. Okay, so there's relative frequency. Now let's do just cumulative frequency. Cumulative frequency. I'm going to run out of room, so I'm going to kind of abbreviate there. Okay, cumulative frequency means we add from the previous column. This is our lowest number, so it stays the same. We have 2 presidents who are 40 to 44. But on the next one, what we do is we add them, and so we have 9 now who were basically 49 or below when they took office. Okay. And then we add that 9 to our next number. So cumulative, we're adding and we're building, right? So now we've got 9 plus this 13 here gives me 22 presidents who were 54 or below. Okay, now I'm going to add 12 more to my 22. And so we have 34 people, presidents who were 59 or under. Okay, then I'm going to add 7. And we've got 41 presidents, and then I'm going to add 3, and we should have our total number of presidents. So 100% of the first 44 presidents when they first took office were 69 or under. Okay, so we should always end at 100. Now we're going to do our percents. So it's cumulative relative frequency, because relative means the percent. I'm going to abbreviate here. So I would do 2 out of 44. So again, my first percent stays the same. And this is the most important column. Okay. Then I would do 9 out of 44. Or you could add your percents right here, and we get 20.5%. Okay. I could do 22 out of 44 for the next one. Or I could add these 3% up to get 50%. Half of them that were 54 or below. Okay, and add the next percentage, we get 77.3%. Add the next percentage, 93.2%. Oops, I think I skipped one, you guys. Oh no, I just got off on my rows. And my total is 100. All right, so that's pretty easy. I feel like we could all handle that. Now we got to make a graph, and we got to understand our graphs. So these are called ogives sometimes. It's the same thing as cumulative relative frequency graphs. I've never heard that word before, but ogives. Okay, let's see. So we've got age at inauguration on the bottom. And cumulative relative frequency. So that's adding our percentages. So we start at the bottom and we should end at 100%. Okay. So for our age at inauguration, we started at 40 and we ended at 69. So we'll go from 40 to 70 on our graph. And I'm going to go by fives. I'm going to start at 40, 45, 50, 55, 60, 65, 70. And our percents need to go up to 100. I'm going to count by 20%. So I've got 20, 40, 60, 80, 100. All right, so for 40, we're always going to start at 0 for our first one because it was a range of 40 to 44. So we're going to always start here at 0% for that first dot. Our next dot was once we get to 45. So if I look back here, this is my first dot. Once I get to 45, everybody has to be below 4.5. Okay? So my first dot at 45 is going to be on 4.5. We'll pretend like that's right there. Okay? And we're going to connect it. Connect the dots. Okay? And the next one we've got at 50. So by 50, right here, we go back to our last one. We have 20.5% who are under 50, since this is percentile. So I go 50, I had 20.5, so it kind of jumps up here and connects my line. And my next one, 55, was 50% who were under 55. And my next one, 60, was under 77.3, out here. Okay, and 65, I got to go back one to 93-ish here. Okay, and when I get to 70, everybody was under 70, so 100% were under 70. Okay, so you should start at 0 and end at 100%. Okay, so now we got to use our chart to kind of estimate some things, all right? So was Barack Obama, who was first inaugurated at the age of 47, unusually young? All right, well, let's use our chart. So 47, we want to find 47 on the x-axis. So right here-ish, okay? We want to find where it meets this graph, and then we want to go directly over to the left. And we want to estimate what percentile this is. So what do you guys think? What is that? Let's say 10 is here. My graph is not perfect, probably. Maybe 15. Okay? So we'd say he's at the 15th percentile. So 15% were younger than Barack Obama. Which means that 85% are older. So yeah, that was kind of unusually young. All right, we can also use our graph to go the other way, estimate and interpret the 65th percentile of the distribution. So that means we'd be looking for age. So we're going to use our chart and we're going to go over to 65. Let's see, so here's 70. So 65. And we go down. And we're supposed to get 58. I did that one pretty great. All right. So about age 58, what does that mean? That means about 65% of U.S. presidents were younger than 58 when they took office. All right, so let's see if we can do a couple quick questions. Mark receives a score report detailing his performance on the statewide test. On the math section, Mark earned a raw score of 39, which placed him at the 68th percentile. All right, so what does that mean? A, Mark did better than about 39% of the students who took the test. Mark did worse than about 39% of this that took the test. Mark did better than 68% of the students. Mark did worse than 68% of the students. Mark got fewer than half the questions correct. So raise your hand if you think it's A. Raise your hand if you think it's B. Raise your hand if you think it's C. Raise your hand if you think it's D. E. Okay, good. So that's just, do you understand the definition of percent, right? So you guys all said it has to be better than 68%. All right, and let's look at another graph. Mrs. Munson is concerned about how her daughter's height and weight compare with those of other girls the same age. She uses an online calculator to determine that her daughter is at the 87th percentile for weight and the 67th percentile for height. I didn't write this problem. Explain to Mrs. Munson what this means. Who can tell me what the weight part means? Raise your hand. Somebody who can tell me. Taylor. That is right. She weighs more than 87% of girls her age. But she's also taller than 67% of girls her age. So usually those go together. All right. Okay. Perfect. So number 3. About what percent of calls... Oh, yeah, this actually goes with the graph. Just kidding. So now I'm going to look at the graph. What percent of calls lasted less than 30 minutes? What percent of calls lasted less than 30 minutes? Someone explain to me how I could find the answer to this question. Jake? You mean 30 minutes, but yes, and go up. Whoa, so hopefully as straight as possible here. And then go left. I should use a straight line. Boom. So the correct answer is about 65% of calls lasted less than 30 minutes. So if 65% of calls lasted less than 30 minutes, what percent of calls lasted longer, you guys? 35%. Okay, good. And the last one, which you will see quite a bit and you want to know how to do, how do I find Q1, Q3, and the IQR? Interesting. So Q1, you guys, what percent of the data is that? 25%. So we could probably find that. Q3 is, and then we just subtract, find IQR, right? So we would go up here to this graph, and we would go to 25%. Here's 30, 25. Whoa, that was pretty awesome. So that's supposed to be about 13. Okay, so 13 minutes. And then we go to 75%. There's 70, here's 75. Oh boy, you guys have no idea. All right, it's really hard. That's supposed to be 32. I almost hit that like exact. All right. Then of course for IQR we subtract and we get 19. By the way, all of these should technically have minutes on them. We keep our same units. Okay. Cool. One more thing we got to do, and that is z-scores. How far above average was Malcolm's 86%? Not what percentile is it, but how far above average. So let's look. This is not Malcolm's actual score if he came in late. So here's like the data that supposedly is from the test. This is not our actual test. Mean of 80, okay, median, we've got standard deviation, blah, blah, blah. All right, you definitely want to write this formula down. And I don't think we need these little guys. But what this means, this is a z-score. We are standardizing everything. We're putting it on the standard table, so we're going to compare everything together on one standard scale. So X is your data point, like Malcolm's 86%. All right, X is the data point. And we're actually subtracting mu, which is the mean. So that little Greek symbol U thing, means mu, which is the mean, divided by this sigma, which is the standard deviation. That's what we divide by. Okay, and we're going to see how far above or below the mean we are. So Malcolm had a score of 86. Okay. According to the data on the previous page, the mean was 80. So I'm going to subtract 80. And according to the data on the previous page, the standard deviation was 6.07. Okay, so that's always how we're going to standardize this. And we end up getting 0.99. So he was almost 1 standard deviation above the mean. That makes sense. If the mean was 80, he got an 86, and the standard deviation was 6.07, right? 1 above is an 86.07. So that's called a z-score. So one more example here, and then you guys have a little practice problem. So in 2012, the mean number of wins for teams in Major League Baseball was 81, with a standard deviation of 11.9. Find and interpret the z-scores, okay? So we want to standardize this. What does this mean on the standard scale? And this will start to make a lot more sense to you because we're going to do a lot with z-scores, okay? So the New York Yankees had 95 wins in 2012. So we are going to find the z-score. You need to memorize the formula for z-score, all right? So it's the data point that you're given, so that's 95, minus the mean, which they tell us is 81, divided by the standard deviation, 11.9. And we get 1.18. Okay? So again, we want to interpret it. So the New York Yankees were 1.18 standard deviations above the mean. When we standardize, you guys, the mean is 0, and every standard deviation is 1. Goes by 1, 2, 3. Okay. All right. So now we got this other team right here. The New York Mets didn't do quite as well. They had 74 wins that season. So we take the z-score. We have 74 minus 81, because that was the mean, divided by the standard deviation. Okay, you should get negative numbers when someone is below the mean. So this is a negative 0.59. All right, so when you explain it, you can just say 0.59 below the mean. I should say standard deviation below the mean. All right, so that's z-score. A quick intro to it. We will do a lot more with z-scores.